All right, this lesson was requested for those who are away for the calorimetry. So I've copied and pasted the lesson into our homework question help section of our OneNote, so you'll find all my scribbles here after we are done. So let's work through this. We'll see if we can get this done in like 10 minutes. So quick information about law of conservation of energy. We just have to remember that it means basically there's energy is never created or destroyed, just changes forms or transforms. So we're looking at in calorimetry is just looking at basically heat transfer. In chemistry, chemical reactions, but for us in physics, we're going to be talking about between objects. So we're just saying first law of thermodynamics, during any interaction between a system and surrounding, the amount of energy gained by a system must equal exactly the amount of energy lost to surroundings. So we are just going to use our Q equals mc delta T type formula to do that. But if we take a look here, a letter for thermal energy is Q. So essentially what this is saying is heat loss is equal to heat gain, is Q losses plus heat gain should equal 0. So that's what we do down here, which is the same as saying Q lost is basically like a negative Q. So plus Q gain is equal to 0. Then I can say Q loss is equal to Q gained. If we think back, Q equals mc delta T, which then means that basically the mc delta T of our loss is equal to our mc delta T of our gain. And we're looking at basically that with equilibrium. And delta T, of course, can be split into final minus initial, will give you your difference. So generally our hot side loses energy, our cold side gains energy. So hot side will be a negative, and cold side will be the positive. So let's take a look at example 1 here. I'm just going to do it off to the side. So we've got 0.4 kilogram iron horseshoe, initially at 500 degrees, dropped into a 20 liter bucket of water at 22 degrees Celsius with the final equilibrium temperature. So as soon as you see it says equilibrium temperature, we are going to be using our Q equals mc delta T, but we need to put an equilibrium. So that's this formula right here is what we're going to be using. So we go, let's see, a negative mc Tf minus Ti. I should really get a writing pad for my computer, but that's alright, mouse is working. mc Tf minus Ti again. That should be a bracket. Horrible bracket. There it is. Horrible brackets. Alright, so we got basically we're going to have our hot side and our cold side. So we're going to have our negative side, which is basically our hot. Alright, so we got hot, and we got cold. Okay, hot, we've got basically M, C, TF, and TI. Okay, and that's our hot, and that's our cold side. So on the hot side, our M value, mass, is basically it's an iron horse, 0.4 kilos, so it's 0.4. Right. On cold, and it's initially at 500 degrees Celsius, so that's our initial T, 500 degrees. There we go. Oh, yeah, that's fine. On the other side here, basically we've got a 20 liter bucket of water. 20 liters is 20 kilos, so 20 kilograms. 20 kilos. We'll get to our C's and everything shortly. TF we don't know, but we know 22 is our TI, so that's 22. There it is, 22. So that's 22. This C value, I said we never need to memorize it. We're always just going to go back to our table. And the table, if we go back to a previous lesson, quickly race back to a specific heat, we've actually got this stuff in our table right here. There it is. So water is 4180. And it was a iron, which is 460. So that's our two numbers there. So that's what we're going to go back to. So we go back to, there it is. So 460 for iron. And 4180 for water. And I'm hoping when you're writing this, you are a little bit simpler. Oh, there it is, 4180. TF, it says it's getting to equilibrium temperature, so that means basically your TF on one side should equal our TF on the other. So we just chuck an equal sign across, saying that they both equal each other, and that's what we're hunting today. So we put this all into our formula now. So we got basically we got negative 0.4, right, times 460. Bracket TF minus 500. And then equals, so 20, 40, 80, 40, 20, 4180, and then basically kind of TF minus 22. And yeah, kind of, there you go. All right, absolutely horrible writing. But we get all this together. We should start multiplying things together, and I really should have had my calculator ready to go, but let me just pull it out of my bag very quickly. So you're just going to use your calculator. I'm just going to calculate the first side, which is basically 0.4 times 460. And I get 184, so it'd be a negative 184 on this side. Bracket TF minus 500. Close bracket on the other one side is 20 times 4180 is 8360. Sorry, 00. 83600. That's horrible. TF minus 22. And because I'm going to, and that's 22. And because I'm going to try and keep this a little bit shorter, I'm going to say at this point it's just straight algebra. Multiply the outside into the brackets. Collect like terms, and in the end, basically from memory, this should be about 23 degrees, give or take, from what we did on the board. So you'll end up with the final TF equals, and then basically kind of, which kind of makes 23 degrees kind of makes sense because it's a heap of water with a very high specific heat capacity and a little piece of iron. Yep, with a low specific capacity. So that means basically this will suck up a lot of heat without changing the initial temperature that much. So 23 degrees does make sense, but it should be, your final temperature should be somewhere between 22 and 500, because it's, of course, going to come to an equilibrium between these 2 points. This next question, I'm not going to do it here on the page, but this is just a bit of an idea, right? So you got steel, again, spoon, 5 grams to put into the fridge until it's 40 degrees Celsius, and placed into a 250 milliliter, which is a cup of very watery black tea. So a reminder, you change that to kilos, you're changing that to kilos, right? What is the initial temperature of the tea if the equilibrium reached 64 degrees? So your initial temperature should be higher than the 64 degrees because that's the equilibrium. Just making sure you're keeping track of your hot and cold sides. So that specific heat capacity you use in equilibrium, okay? We then take it another step further because in this case here, everything that we've done is all in the same phase. So basically our solids stay solid or liquids stay liquid. Whereas down here, we actually start looking at basically how phase changes, or basically what happens. And so we got specifically latent heat of fusion, latent heat of vaporization. Okay, there's our definitions for them. And we've actually got a table of values for different elements or substances as well. Making sure that we know which one is fusion, which one is vaporization. Fusion, vaporization. Alrighty. We're going to use this formula here. You'll find it in your formula sheet. It looks like this, Q equals ml. And you just have to recognize, all right, am I talking about vaporization? Am I talking about basically liquid to gas or vice versa? Or am I talking about fusion? Am I talking about gas to solid or vice versa? So this first one here, I'm going to do example 1 again. Okay, so we just have basically Q equals M L, and this is basically how much energy is needed to boil 150 grams of water. So if we're boiling, we're at vaporization, so it's LV. So in this case here, Q M LV. So Q we don't know. M is 150 grams, so that's 0.15 kilograms. Okay, and because it's water, just look at water table, and we look at vaporization, which is here, so it's 2.26. 2.26 times 10 to the 6. And then we just chuck it all in the formula, and so we get Q equals 0.15 times 2.26 times 10 to the 6, and we end up with 0.15 times 2.26 times 10 to the 6, coming in with 339000. 0, 0, 0, and because it's Q, it's got to be joules. So there's joules, and that is our answer for question 1. So the whole idea is that basically you'll add energy to change it, to increase the heat, but as soon as you hit that vaporization state, it actually takes an extra little bit of energy to force it to change state. So say water, you'll get to 100 degrees Celsius. From 100 degrees Celsius of liquid, or 99.99 degrees Celsius of liquid, then to get to basically a full water vapor, you'd be using 2.26 times 10 to the 6 joules per kilogram of that liquid. So to change state. So that's 1. 2 is a little bit different. I'm not going to do all of 2, but we have basically 2 is an 845 gram bar of ice, initially at negative 25 degrees. Energy is added until the system reaches 39. So it's a tiny little question, but it's actually got multiple parts to it, because we have to recognize that we are using specific heat capacity, so Q equals MC delta T, and we are also using basically our specific latent heats, Q equals ML. So because we are going from negative 25 degrees, right, Celsius, then basically from there we actually, without any phase change, we get to 0 degrees Celsius. And then basically we have a phase change at 0 degrees Celsius, and then from there we go to 39 degrees Celsius, again without a phase change. So we have here basically kind of at this section we've got a Q equals MC delta T to get our Q. Here in the middle basically we've got a Q equals MF, or ML, sorry. And it's MLF because it's fusion, okay? And then basically here again, this section, we have another Q equals MC delta T. Okay. This section here, our mass is 845. This section, our mass is 845. This section, mass is 845. So that's all good. That's all the same. Here, we actually have our C value of ice. Here we have our C value of water. So again, if I go back to our content library, so ice actually has a different C value than water. So there's ice is 2050, liquid water is 4180. So we can't combine them together. We have to do those two calculations separate. Back to the collaboration space. So we have one C value here, a different C value here. We've got to do them separate. And then delta T on this side is 25 degrees because that's from negative 25 to 0. Delta T on the side is 0 to 39. So what we have to do is we have to do it in 3 separate steps. So basically, essentially, we have to do step number 1, basically to kind of get our first Q value from here to here. Step number 2 to get our base, not 3, 2, let's try that again. 2 over here to get our basic phase change Q value. And step number 3 is to get our final 0 to 39 degree Q value. And then we're going to add 1 plus 2 plus 3. Okay, and then basically, so total QT equals Q of 1 plus Q of 2 plus Q of 3. And that's how we get that one. So this one here is probably where something like this is worth maybe 1 mark, and it'll probably be even a multiple choice question. All right, this here basically might be a paper 1 question worth maybe about 5 marks, maybe 1 for recognizing the thermal sections, blah, blah, blah. 1 mark for each of these sections, and maybe 1 mark for the final answer. That's kind of what you're looking for. Otherwise, that is our time. I did it in 14 minutes, so a little bit farther, but enjoy.